So last time we calculated the multiplicity function for an n-spin system, and we saw that it gave us really large numbers. Um, and based on that, we calculated the probability of encountering a certain number of spins, and we saw that it was could be approximated fairly well by a bell curve. And then we said that since these multiplicities were so large that it makes sense to take the natural logarithm of them, and then we introduced a function s, which is k times the natural logarithm of the multiplicity. So that was for the n-spin system. This time we're going to look at another system where we can calculate the multiplicity and investigate this s function and some of the conclusions that we can draw about it. We're going to look at a really simple model of a solid, the Einstein model of a solid, where each atom is connected via an elastic bond to its 6 nearest neighbors. Now, according to quantum theory, those elastic chemical bonds have energy levels that are evenly spaced and must therefore be some integer multiple of the energy step epsilon. So a bond could have 1 epsilon or 2 epsilon or 3 epsilon or 4 epsilon of energy. So the energy per bond is a certain integer times epsilon. So let's say that's little n times epsilon. So the total amount of energy in the solid, well, that's going to be the sum of all the n epsilons. And we're going to call the sum of the n the sum of the n. That's the total number of quanta in the solid. It's just adding up the integers. And so you multiply that by epsilon, and that gives you the total internal energy. So as a for instance, so let's say this is the energy of a solid, and it's split up between a number of bonds. So I just put a little space there, and that's where we're going to partition this energy through a number of bonds. So the first bond is going to have 2 epsilon of energy. I counted the dots previously. I hope I did it right. There's 7 epsilon of energy for that bond, 6 for that one. This is the most energetic bond, 8 epsilon and 5 epsilon. So this is just a little example here. And so this way of partitioning energy up over chemical bonds, we want to count the number of ways that we can do that, because that ultimately is the multiplicity of a macrostate. So there are, if you like, this is like a list of Q symbols, right? Because there's Q dots here. So there's Q identical dots, and then there's n minus 1 partitions for n bonds. So for instance, with 1, 2, 3, 4, 5, 6 bonds, we needed 5 partitions. So we can just count this using combinatorics, because we've got this many symbols. And so with this many symbols that we have, we want to know how many ways we can put them in a group of Q. So that's given by a permutation. So that's Q plus n minus 1. Pick a group of Q. Now, because the n minus 1 partitions are all identical, there's a degeneracy then in the permutations, and then it turns out we need to divide by n minus 1 factorial. So according to the rules of permutations, this is Q plus n minus 1 factorial over Q factorial, but then we get this extra degeneracy factor of n minus 1 factorial. So that's the number of ways to take Q quanta of energy and split them up over n bonds using n minus 1 partitions. Now, because both Q and n are very large, we can approximate this. We could just drop the 1, and we could say, okay, it's just Q plus n factorial over n factorial Q factorial. Now, according to the simple Stirling approximation, we can approximate these factorials as exponents. So this is going to be Q plus n over e to the Q plus n power. And then we're going to have n over e to the n for n factorial, and q over e to the q for q factorial. Now the first thing that happens is that the e to the q plus n in the numerator and in the denominator both. There, I just moved some things around to make that a little easier to see. So the first thing that happens is that there's an e to the q plus n in the numerator, and then there's an e to the n plus q in the denominator, and they cancel each other out. So I get down to this using the simple Stirling approximation. I'm now going to factor a q out of both of these terms. So it'll be q to the q plus n. I'll be left with 1 plus n over q, still to the q plus n power. Now the q to the q will cancel this out, just leaving q to the n. So I've got q to the n over n to the n. And then operating on this one a little bit, what I'm going to do is, first of all, I'm going to say that q is a lot bigger than n. Let's roll down here a bit more. So because q is much, much bigger than n, then I'm going to say this is about 1 plus n over q. I'll just drop the n and just say that's q. But then in the limit as n gets really big, or rather, I'm sorry, as the limit as q gets really big, this is actually the exponential function, e to the n. So I'm going to replace this bracket with e to the n. And so I come up with this expression for the number of ways of distributing q quanta over n bonds. It's just q e over n to the n. Now, in terms of the internal energy, because U is QE or Q is U over epsilon, and remember that's just the, I shouldn't say that's E, that's epsilon. That is just the energy per bond quanta. Then we can say that with using the previous expression and substituting this in for Q, we're going to get U times E, and that's 2.71828. Then this is epsilon, to be careful, and that's the energy quanta. And then this is n, which is the number of bonds. And all of this is to the power of n. All right, so that's the multiplicity function for the Einstein solid. Now, what can we do with that? Well, we're going to study the equilibrium of two solids brought together. The total number of bonds, and the two solids, the two identical solids, two pieces of the same solid, A and B, are going to be brought together. So the total number of bonds, if they're put together, will be just the sum, Na and Nb, and the internal energy will also be additive, UA plus UB. Now that means, and we'll use this later, that the energy in block B is U minus the energy in block A. So we have two blocks of steel, we put them together. This is the total number of bonds, and this is the total energy. Now what about the multiplicity? Well, by the counting principle, remember this was based on permutations, if solid A's got this much multiplicity, this much degeneracy, and solid B has that much, then the multiplicity is actually the product of those two. Right? So if there's 8 ways to do solid A and 7 ways to do solid B, then there's 56 ways to do solid AB. That's just known as the counting principle. So let's study now the equilibrium of these two blocks put together. Now, the most likely state we've seen is one where the multiplicity is a maximum. So that means it's maximum with respect to a number of variables, including with respect to the internal energy, because we've written the multiplicity as a function of the internal. Okay, so the multiplicity is a maximum. Now, we've written this using the counting principle as the product of those two multiplicities. We'll now do the result we just derived, and we're going to differentiate with respect to UA. And so this was EUA over NA epsilon to the NA. And then this is going to be EUB, but I'm going to write that in terms of UA. So that was the internal energy in block B. All to the number of bonds in block B. So all of this has to be differentiated now with respect to the UA variable. So we have to use the product rule and the power law. It's a little messy just because there's a whole bunch of symbols there, but really it's quite simple calculus. So we use the power law here, and then this one remains unchanged. But we have to multiply by the derivative of the inside. And then this term remains unchanged, because I'm not differentiating it. I'm going to write that as UB. So that's derivative of first times second. Of course, I still have to add first times derivative of second. So I'm now differentiating this with respect to UA. So that's going to give me, well, we have to do the power law here. Reduce the exponent by 1 and then multiply by the derivative of the inside. Differentiating with respect to UA, I'm going to get a negative 1 there with the minus 1. Now there's a whole bunch of like terms here that I can factor out and then just cancel. And so what's going to survive is, because the NA cancels out, well, here, maybe I'll just cancel that out here. So NA cancels and the NB cancels. And I could get rid of the E's and the epsilons because they appear in both terms. And then most of this appears. This appears to the power NB. Here it appears to the power NB minus 1. So I can factor out NB minus 1 of both of those. Maybe I should do that. So I factor out NA minus 1 of those. Same thing here. Factor out NB minus 1 of those. And so what I'm left with here is I'm left with a UB, just one of these terms. So it's E UB over NB epsilon. And then I can also take out, let me take out the E over epsilon term. And so I'm left with one of these, and then a minus 1 in this term, and then one of these. So there's another E over epsilon that gets pulled out and canceled, because I can divide through by this, because it equals 0 on this side. And ultimately, I get the much simpler expression that UB over NB minus UA over NA is 0, so that at equilibrium, it must be that the internal energy per bond and ultimately per atom is the same. So that's our equilibrium condition. All right, so we said the derivative had to be 0 because the multiplicity had to be maximum, and that tells us that for when the two solids reach equilibrium, the energy per bond, or the energy per atom, because they're proportional to each other, will be the same. So we can look at this in a different way using our S function. S is proportional to, although not directly proportional to, the multiplicity. And putting in what we derived about the multiplicity earlier, there's a couple of symbols that are missing here. There's E to the 2, which is 2.71828, and it's supposed to be to the power of n. So first of all, what can we say about the S function of the combined system? Well, that'll be the log of the combined multiplicity. We've seen that by the counting principle, the combined multiplicity is multiplicative. But then by log properties, this is the sum of the logs, and this is the S function for solid A and the S function for solid B, so we see that the S function is additive. Now, we've said that, using the laws of probability, that an equilibrium state corresponds to the state of maximum multiplicity. If multiplicity is maximum, then this S function is as well. So if it's a maximum, then its derivative is 0. So the SAB function we just showed was SA plus SB. So that is the derivative for the first block of material, and then there's the derivative for the second block of material. But since B and A are related by a minus sign, the partial with respect to energy A is the negative partial with respect to energy B. So I get, substituting that in, this expression here. But what are these derivatives? So I've got to differentiate this now. Well, that's a logarithm. Again, the derivative looks a little ugly because there's a lot of variables here, a lot of symbols. But there's only one variable, right? We're just differentiating with respect to the internal energy A. So it's K. The N comes down in front. Then we just have, that's just by the log property, by the way. Then we just have to do the derivative of log. The derivative of log is 1 over x, so that's just the reciprocal of this argument here. And all these, by the way, should be NA. And then you got to multiply by the derivative of the inside. I'm doing the derivative with respect to u, so I just get E over NA epsilon. And so that simplifies to K NA over UA. So I expect when I do the derivative on the second block, it'll again be K NB over UB. So the equilibrium condition implies that because this function S has to be a maximum, I should put 0 here, that these two quantities are the same. Derivative with respect to, let's try and do that again a little more neatly this time. My pen sticks sometimes. So that these two things have to be equal, so that means KNA over UA has to be KNB over UB, which establishes again that, well, this is just the reciprocal of what we showed earlier. So flipping it around to make it easier to say, the energy per bond, or the energy per particle, must be the same. Now remember, n was the number of bonds, and that's actually 3 times the number of atoms, because each atom has 6 bonds to all of its neighbors. Well, we started off this course by saying that the property that's equal when two systems are in contact with each other and reach equilibrium, that was the temperature. So when those two blocks are at equilibrium, it should be the temperatures are the same. So what that's telling us is we have a new definition of temperature. We have, if you like, a statistical definition of temperature related to the statistics of microstates. The temperature, well, we'll write its reciprocal in this way, is the derivative of this S function with respect to the internal energy. And you can see that because this S function has the same units as the Boltzmann constant, joules per Kelvin, when you divide by joules, you get reciprocal Kelvin, and that's why we write it as 1 over T. Well, that's interesting. That's now temperature has a sort of a firm basis in physics with this statistical definition. And so what we've got then, just to recap, is that when we take two blocks of solid and bring them together, and when they reach equilibrium, we stated earlier in the course the experimental fact that they reach the same temperature, and we talked about a number of ways of measuring temperature. We said at the time that temperature was a measure of the average energy per particle without really defining it explicitly. Well, we now have that definition, right? This is the precise definition of temperature in a statistical sense. So we can say another thing when it reaches equilibrium. This we established by the laws of probability. The multiplicity omega is a maximum. And that tells us, of course, that this S function is also a maximum. So this applies to the equilibrium between these two blocks of solid, for which we've been able to calculate the multiplicity function, and therefore this S function. Now, this S function, it's time to stop calling it the S function and figure out what it is. Well, we just finally wrote down the statistical definition of temperature. Right? Let's pretend the volume's constant, and therefore internal energy is only varying with temperature, a constant volume. So we could write it as an exact differential. So this was, if you like, our statistical definition of temperature. I'm just going to replace the partial derivative with an exact derivative, and then I'm just going to write ds as a differential. If we apply the first law of thermodynamics, you remember that? Remember U is Q plus W? Well, this was an expression for W. We write it in differential form, which is true for reversible and quasi-static processes. If volume constant, then du is dq, so I can put that in there. And then we get back to the thermodynamic definition of entropy. So, this function S, no surprise, it's our old friend entropy. And we had originally defined ds for a reversible process as dq over t. We now have a statistical definition of S in terms of the number of microstates for the system. Now, all the conclusions that we drew earlier about thermodynamic entropy apply to this statistical definition. And this really completes the picture for us on entropy, and we now have to begin the multi-year process of trying to reconcile these together. I've shown in one limited case that they're equivalent, but it turns out in all cases that they are. Now, this definition of the F function in terms of statistics is really useful because suddenly it relates this abstract concept of entropy to something fundamental, something microscopic, the microscopic property of the system. But it isn't exactly easy to calculate. It's much easier to calculate the entropy change for processes using the thermodynamic definition. So that's why we started there. But now we're finally going to make contact with the microscopic definition and say that they're the same. At this point, we're going to take a very simple system and show that the entropy change in both cases is equivalent. We can only do that for simple cases because the statistical definition of entropy doesn't lend itself very well to calculations. We'll pick it up at that point in class.